At this time, we're about to tackle the divergence theorem. This is our next to the last lesson for the entire course, so I hope you find it worthy. So, the divergence of a vector field is a derivative of a sort. Recall finding a divergence in I think it was lesson 1 from unit 5, as a matter of fact. So it measures the rate of flow per unit of volume at a point. For example, how much flow per cubic foot. So a field where such a flow doesn't occur is called divergence free. That's something like a rock is divergence free because it's not moving, or a brick. Anyway, the flow per unit of volume across any point is 0 for a rock because the rock doesn't move. That is, if the rock is the vector field. Now, if you got fluid flowing around a rock, that's a different story, but the rock itself is divergence free. Okay, so if we got a vector field described as some f of x, y, z equals mi plus nj plus pk, m, n, and n are all differentiable functions of x, y, and z, then the divergence is given by, and I think we had this earlier, divergence of our vector field f is the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z, thinking the partial of m with respect to x. In other words, the partial of the I component with respect to x is what it boils down to. Partial of the j component with respect to y plus the partial of the k component with respect to z. That's the divergence. So, it's a three-dimensional version of Green's theorem, is our divergence theorem, which is coming down here. Here we got to think about the condition that a surface S is closed, meaning that it is the complete boundary of a solid Q. In other words, you couldn't have a hemisphere because the surface has to be closed. It has to enclose a solid. So the theorem gives us a relationship between the integral over a solid region Q and the surface integral over the surface S of our solid Q. And here's what it states. Theorem 15.12. The divergence theorem, also known as Gauss's theorem. So, let Q be a solid region bounded by a closed surface S, oriented by a unit vector pointing outward from that surface, from Q. If F is a vector field whose component functions have continuous partial derivatives in Q, then the double integral over the surface S of vector field F dot normal vector n ds is equal to the triple integral over the solid region Q of the divergence of vector field F dv. And of course, you know, the solid would dictate what our limits of integration are, and the dv, well, who knows, we might wind up in spherical or something, you know. You might recall some test question saying something like, well, how can you represent dv? And there's really an infinite number of ways. Recall any Jacobian will work. So, let's, whoa, we didn't mean to go that fast. Let's verify the divergence theorem by evaluating this version as both a surface integral and as a triple integral, this one, say. And of course, we know from Gauss's theorem that that should be true. And S is the sphere, x squared, I guess, should be true under nice circumstances, right? Whose component functions have continuous partial derivatives. There, you know, we needed to know that. So, S is the sphere, x squared plus y squared plus z squared equals a squared. And the vector field is f of x, y, z equals z times k. So we'll do the triple integral first. Notice that for this vector field, what is the divergence? Well, it's the partial of the I component with respect to x, 0, plus the partial of the j component with respect to y, 0, plus the partial of the k component with respect to z. Partial of z with respect to z is 1, so the divergence is 1. So what we have is this integral, since this is our surface, it's our solid region Q, so the integral of the solid region over the solid region Q dV is just the volume of the sphere, so we get this real nice answer for pi a squared over 3. If that doesn't show up very well, maybe it does there. Right? So it's just the volume of the sphere, that's it, that's what this is. Remember, this is a 1 here, right? That was a divergence, 1 dV, so, alright, volume of the sphere. Well, let's try the surface integral, probably not quite as nice, but let's try it anyway. So, the sphere consists of the upper surface, z equals square root of a squared minus x squared minus y squared, and the lower surface, z equals the negative of the same. Constructing our function g of xyz, which is z minus this, right? Take any of these and make it into a function. The normal vector is orthogonal to the level surface. Thus, this, the level surface, the normal vector would be orthogonal to this, and so we'd say, all right, then let's find that normal vector. Well, the partial derivative of this with respect to x is, oh, get this, partial of z is 0, so we don't have to worry about that. We're going to have, this is a squared plus x, minus x squared minus y squared to the 1/2 power, take the derivative, we get 1/2 times that to the negative 1/2 power times the derivative of the inside function, which is negative 2x. So that negative and the negative in front will cancel out, and we're just going to have x over the square root of a squared minus x squared minus y squared. All that times I. There we go. And partial derivative of this function with respect to y, similar, right? Not much different, only the derivative of the inside function is a little different, but other than that, it's exactly the same. And the partial derivative of this with respect to z is just 1, so plus 1k. And so what integral do we want to evaluate? F, which recall, f is z times k. So z times k dot this normal vector, right? And so if we dotted these two vectors, the only thing we get from that is z. So region R of z dA, now think about what our region R is now. We are looking at a circle of radius a. And so here's our z. This is a circle. Remember, z equaled this. Somewhere along the line we saw that. And so we're replacing that. And dA, of course, and region R, since it's a circle, if we had half a brain, which leaves me out, I guess we'd want to change it into polar coordinates, of course, where circles and things like that involved. They're much nicer in polar, so R goes from 0 to A, right, inside diameter, outside diameter. Theta goes from 0 to 2 pi. Our A minus x squared minus y squared is really A minus r squared, so that's the square root of that, r d theta. Well, let me see, how do we integrate that? Let u equal A minus r squared. And then you should see how that comes about. This is u to the 3/2 when you integrate it, times 2/3, and then don't forget to multiply by the inside, or actually divide by the inside. Well, you'll get it. You get it. This is just almost a trivial problem here to work this out, now that you know something about integration. So if you do that, it will yield a value, trust me, 2 pi a cubed over 3. Of course, the lower surface, recall now, this was, where is it? This was the upper surface. And so the lower surface, if we took the time and trouble, we're not going to, would be, hey, you could get it from symmetry. The lower surface is the same result, so we will get 4 pi a cubed over 3, the volume of the sphere, and it sure was easier to do it the first way.